All right, well, welcome to the very, very final units of our power circuit and transformers block. And it is three-phase transformers. All right, so we talked in the last couple of days about single-phase transformers and then some special transformer configurations between using the auto transformer and using, parallel banks of transformers, and talked about that distribution transformer. Well, now we're going to talk about what we're probably going to see a lot of is three-phase transformers. And kind of some of the sciencey stuff behind it, but in reality, this should be more of an exploratory learning block where you're just kind of putting everything that you previously did together to kind of understand, what's going on here. And again, these transformers are so important to our distribution system that knowing and understanding them, knowing how to troubleshoot them because you understand the system. You are a warrant officer, so you are a systems integrator. You need to know the system. Knowing what's going on in there kind of helps you deduce and troubleshoot some problems that are out there in the field. So the three-phase transformer block is really just about the connections and some of the science behind the connections and some varying connections. So I don't want you to look at the three-phase transformer like this one set of primary windings and one set of secondary windings. I want you to look at it like three individual single-phase transformers that we're now going to put together. All right, and again, we're going to be using the three-phase transformer block here, and that is going to be the principal source for this last day, and this is going to require three-phase power. So again, we're going to either be generating our own three-phase power from here, or depending on your class, we may set up a common bus. The instructor will set up a common bus above you, and then you will just tap down from the common bus and get that three-phase. All right. But one of the first things I want to talk about is, again, let's look at this like three separate single-phase transformers. All right. Now notice, again, I'm drawing the distribution transformers that we talked about in Unit 8. And these are also the exact replication of what you're seeing over here on this three-phase transformer trainer. However, again, it's rotated 90. So when you actually start doing the connections, you're not seeing it perfectly like this. Each one of these individually looks like it's going into each other, so it's a little counterintuitive. So it's going to be a little bit harder to visualize. However, know and understand that all we're doing is we got three single-phase transformers here. And now, one of the first things that we're going to talk about is how do we connect these single-phase transformers in a way that's going to give us a desirable output. And we've already actually talked about these connection methods, but now we're talking about it in different perspectives. So now we're talking about how do we connect the primary side, and also how do we connect the secondary side. All right, and so we had talked before about Y connections and delta connections. Okay. All right, so we've got our Y connection and our delta connection type. Now, what that means is that's how we are making the physical connections in reference to the coils that we are doing. And if you remember back to this generator down here, and I showed you these three coils here, and we connected it in a Y configuration that looked like so. All right, we took three individual coils and we connected them in such a way that it looked like this by putting all of these points to a common point, and then these points they ended up going up and being what we were measuring the voltage off of by making a common node there. Now we could have done the same thing hooking it up in delta. Right? Because it's all about how we're making these connections. Well, this same principle applies to the transformers as well. And with transformers, though, now we're referencing both the primary side and the secondary side. All right, so what does that mean? That means that we're going to talk about four specific connection types with three-phase transformers. Those four connections are going to be Y, Y, Y delta, 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 Y. All right? And, I mean, you kind of pick it up, right? Y connection, delta connection, delta connection, Y connection, delta connection. It's all relative to the connections, and it's just those two sides. So why would you connect Y, right? Why would you connect Y? Why would you connect delta? Well, it all kind of boils down to what is the available service that you have, what is the voltage that you need, what's the output that you need. Because these different connections are going to have different relationships between voltage and current, such that we already learned about in a Y circuit when we were in Unit 6. We learned that in a Y connection, the phase voltage is 1.73 scaled down from the actual line voltage, right? V phase equals V line divided by 1.73. All right, the phase current is the same, line and phase, in a Y. In a delta, you had that same consistent voltage, that one voltage, unless you had some special stuff going. You had that one voltage. However, there was a 1.73 degree difference between phase current and line current. So these things transcend down now to larger scale connections. So what I want to first talk about is just identifying connections. All right, and so what I want to do is let's draw. This is power lines. I'm just going to draw power lines here. Pretty little trees. Okay. Now there are some kind of simple ways or some easier ways that you can recognize some of these connections. One of the easier ways to see that Y connection is seeing that there is a common point. Right? You were seeing, like when we did this physical connection, I just made that one common node. This is one common node. On this delta, you don't see any common nodes between all three coils, not at all, right? So that's a good indicator. Well, in a Y system, that common node is that neutral point that now becomes, when we reference all those vectors at 120 degrees here, and 120 degrees here, 120 degrees here, when they're in that connection, all those vectors come back and you get that 0 point in the middle, that neutral element, because of vector math, all right? Well, that would be, if we took this, let's say, doop, 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 up here to A, and we're going to take this to neutral. Then we're going to take this, I'm going to come over here, and I'm going to go doop, doop, up to B. Then I'm going to take this to neutral. Then I'm going to take this, you can probably guess where I'm going with this, over to C, and bloop, over to neutral. So what is my commonality there? Well, I took one side of those coils, one side of the windings in each one of those transformers, and I brought it to that neutral point, to that common node, to that connection. Whereas the other three parts of the coil went to other phases, which means I did this right here with this connection right here. Okay? So, why would I do that? Well, why? All right? It's all going to come down to availability of voltage, what you need, and what you have. And one of the great resources for that is inside of the Blackboard module, you should see a file that's Leclerc Electric Transformer Trainer. And on it, they have all of their their organizational specific wiring methods for when they do what and why. Okay? So it'll say, well, if you have this voltage, make this connection if you need this voltage. If you have this voltage and you need this voltage, make this connection. If you have this voltage and you need this voltage, make this connection. All right, and it even goes into the specifics of where on the transformer, on these little single phase cans, because now you could look at this configuration right here, just like this. That's all that is. We got 3 single phase transformers, and you've probably seen that before too on that pole, right? Got our pole right here, coming down, like so. We got our bracketries here, and we see our little H1s here, right here, and we got our wiring going across there. All right, and now let's say that these ones are ones that have 2. Make it easy for you. Well, right now, because I just drew H1 and H2, I'm just talking about this part, the primary connection. So this all that I drew here would be the same if this is A, B, C, and D. Oh, D. N. All right. Would be the same as me going, okay, well, I got my jumper to here. Got my jumper to B. Got my jumper to C. And then these jumpers are going over here to neutral. Like so. That would be the equivalent of this, which is the equivalent of this connection. All right? So now that's the Y side, and I can do the same thing with the delta side. All right. The difference is the delta is actually, I don't want to say it's easier to conceptualize, but I mean, I always just remember that if we look on that transformer, if we look on those coils, I know that a transformer and a delta connection is going to be A to B, B to C, C to A. I mean, that's just, those are the connection points. That's what you have. You have A to B, B to C, C to A. And what I mean by that is if I call these the coils here, and I say this is A, B, and C coil, I see my connections. I mean, I'm going to have A to B, B to C, and C to A. So in this case, if I know that, I'm going to connect this A to B. I'm going to connect this B to C, and I'm going to connect this C to A. Notice what it doesn't have? We're not hooking up that fourth wire. We don't have a common point in there. There's no common node. It's just A to B, B to C, C to A. All right? Now, what does that mean? Well, we know from the previous class that the delta connections in a three-phase circuit have that different varying relationship. They have that line voltage equals the phase voltage. But line current now is the phase current times 1.73. And so what that does is if you have these varying connections within a transformer, you can actually create phase shifts between the primary and secondary voltage. And you'll see a spot in there in the reading about something to the effect of 30 degrees. I don't want to get into like some deep, dark vector logic here. However, that 30 degrees phase shift between 120 degree references, which is your voltage, is actually what the deep dark science goes back to why 1.73 is a factor in your resultant. It's going to cause you to have current and voltage differences depending on your connections that are going to be scaled by the square root of 3. All right, and we'll go through, you're going to do it in the lab. Just know and understand when you read about that 30 degrees phase shift, it goes back to unit 6 when I explained to you what's the origins of 1.73. Okay, and the origins of 1.73, just again, if we have one vector here that's V, another vector here that's V, we know they're 120 degrees out. Okay, I bring my resultant here, I cut it in half, I know that that is going to be 60 and 60, that's a 90, that's a 90, that's a 30, then that I know that's 1, square root of 3, that's 2, V equals 2, that means this resultant vector is 2 times square root of 3 because I got square root of 3 here and square root of 3 here, so 2 square root of 3, and I know that 2 equals V, which means I'm going to substitute V for that, and I have V phase square root of 3 equals V line. And when you do the arctan of this stuff, you're going to come back with that means it's going to be V line at a 30 degree phase shift. So again, that's why when we talk about these phase shifts inside of the transformer, when you read about it, it all comes back to the 1.73 vector math and that 30 degree resultant vector that you're getting between these two right here. So again, not super relative, not super important, but just understand if you want to know the why behind the math, that's leading to some of the why behind the math. All right, so we said on the primary side, that was a delta. And again, that was the equivalent. Let's see if I can fix my little drawing here. All right, that was the equivalent of this going A to B. This one jumping over here because we're still doing B and now going up to C. And this one going C back over to A. All right, so those are the two connection means for the Y and the delta on the primary. Now the secondary side is the exact same thing. All right, there's a bunch of different variations you can have off of this. Bunch of different variations. And you'll see in that Laclede trainer that they have a bunch of different variations. To keep it simple, I'm just going to use the outer windings here. I'm not going to use the inner windings because those can cause some other issues. All right, you can do it. You can absolutely do it. And you can see in the Laclede Electric how they standardize what they do. However, I'm just going to keep it simple. All right, so here, all right, if I'm going to make a common point, I can say this and this. Okay, I'm going to take this to this. Then I'm going to take this down and this down, right? And then I can pull this guy down too. And I'm kind of intersecting all my stuff. But because of how I interconnected these 2 points on the transformer, and I brought this out, say I connected to my three-phase load with these 4 with this configuration, I did a Y connection. all right, because I have that same common point. Now I'm looking at this secondary side. Look at the secondary side. We call this A, B, and C. And each one of them in this same point came down, and they connected to that same neutral point, and they still have their same independent outer values there. So now from this, back to the vector math, if I take a reference from here to here for voltage, so from this point to any one of these, I'm going to be measuring this magnitude of one of these vectors at whatever perspective phase angle it's at. However, if I measure between any two of these, now I'm measuring between here and here, which is going back to that nerd stuff that I did a minute ago that creates a 30-degree offset times scaled square root of 3. So again, why is that important? Well, if you need to be going into a structure that only has single phase, if you only need one singular voltage because it's maybe industrial and you just have one big motor that you need to run, all right, it needs to be that just one single phase balanced voltage, then, you know, maybe the delta is the requirement, and so you hook it up in a delta configuration. But say you have a place that's most normal places, let's say this classroom, and we know that we have 120 volt loads all through these floors, but oh, by the way, we've got this giant AC system over there that's running off 208 volts. So we need that larger voltage for this bigger equipment that we have over here. So we have to have that voltage range. So then we'd know we'd have to do a Y connection. Now there are some instances, and we're not going to go into it, about different delta configurations that you can do that you can actually get that secondary voltage. However, those are not going to be a commonality for you. What's going to be a commonality is going to be delta connection or a Y connection. So I'm just trying to keep it simple. All right. So that was up here we still have our delta. This was a Y connection down here. But what if I want to do the delta? Well, I mean, literally it's the same thing. So I'm going to come down here. I'm going to say A connected, right? So I'm going to go, let's say, A to B, the reference between those, right? Oh, let me do this here. A to B down here, and then I've got, connecting them down to here, I've got B. Oh, erase that. I want to draw this better. This is ugly. And I'm going to end up drawing it not like in the book. All right, so if I want to interconnect here, and I bring my nodes down here, like so, if I take a reference between any 2 points, A to B, A to C, B to C, I've created this continuous loop now with this connection that equates to that. And you can see how this, or you should be able to see how this is what I did right here. So now I got A coil, B coil, C coil, and I can see this continuous loop that I just created within these coils is this. And now the loads coming off of it would be, well, where am I tapping my load off of? Am I tapping a potential difference from here to there, there to there, there to there? It doesn't matter because it's the same between all of them. When we get into configurations in which you would want to get some type of varying voltage off of a delta connection, now let's go back to that auto transformer concept, or maybe the distribution transformer concept, and say, well, what if I tapped off one little spot over here, this little short nugget over there, and reference it from one of these? I'm changing the characteristics of the circuit, so I should be able to get a different voltage, right? Right. However, that's not necessarily as common, and I don't want to kind of go down that rabbit hole. So, again, we're going to talk about 4 different configurations, and you're going to build 4 different circuits in the lab, and you're going to see these square root of 3 relationship differences between if you're going from Y to delta, delta to Y. And it can be confusing. Honestly, it can. So just take your time and kind of understand back to the vector references, and you should be okay. All right? And again, remember to keep it between primary and secondary and look at them independently. Because and when you say, is it Y, is it Y delta, is it delta delta, again, you can look at the primary side independent of the secondary side because they are 2 independent elements. All right, so the last thing that I want to talk about here is an open delta. All right, and an open delta configuration is kind of a special transformer configuration. All right, and it's a special transformer configuration that kind of lends itself to solving problems, which is kind of cool and kind of one of those things, the reason why we talk about it, right? So I'm going to talk about open delta. All right. Now, what an open delta configuration can do for you is if you had these 3 bucket transformers here, and Hurricane, whatever its name is that year, I like to say Hurricane Michael because that's me, right? Hurricane Michael came in, and it knocked out one of those transformers during a hurricane, and you're out there in whatever unit you are, whether you're providing DSURF operations or you're with 249th and you're working for ESF number 3 and working for FEMA, and you're out there trying to say, hey, we need to get power up to this critical facility, and their 3-4-phase transformer bank's gone. The local utility has 2 transformers that meet the same requirements as far as the turns ratio, voltage rating, current rating, all that stuff. But I only have 2 of them. But I need 12208, so I need 3 of them. I need that 3-phase voltage there. All right. So the open delta allows you to say, okay, delta, boom, I only need 2 of these, and I can create this same connection. All right. So how do we do that, though? How do we do that? All right. Well, what we do is we're taking a different type of configuration in between here, and you know what? I'm not even going to draw it for you. Not even going to draw it for you. I want you to see it in the book, and I want you to build it, because it helps kind of understand what's going on right there. When you're taking the power from 3, bringing it down to just 2, and now you're referencing, you can create the same reference ratios with multiple windings. However, what did you do to the equation? What would you do? We go back to this wire, right? That wire that I had, and I said, if I add 2 of them, I get more ampacity, right? I can create more power in there. Well, if I take away a transformer, I'm taking away some material from that circuit, so I obviously have to be limiting some capacity of the system. But by what factor? And what you're going to see is you're going to be limiting by a factor of what I believe is the 57%. I think this is what the book said, 57.7%. And what that is the inverse of the square root of 3. And again, it all goes back to vector math. But the outcome of it is I can create the same 3-phase references on an open delta system using only 2 single-phase transformers. Obviously, there's limitations, and those limitations include that you're limiting your power output by that 57.7% or whatever the book says. I'm pretty sure it's 57.7. So why would you do it? Well, I just told you. I mean, there's plenty of numerous reasons where you absolutely have to have power, regardless of whether or not you need the total amount of power. You need some power. So think about a disaster situation where you just need to get the lights, AC going so you could house some refugees. And it may be a church that uses a whole lot of power, but you only need a certain amount just to get it running, to get people in there and safe and secure. So you don't need the full amount it was designed for. This is an example of that, and that's why it's kind of important to know. But you have to know what you're sacrificing there. You're coming up with a quick solution that's going to provide that power, but you are sacrificing total power capability. So really, really cool connection. I don't want to draw it out. I want you to play with it. By this point, you should be very familiar with the lab bolt system, so you should be able to be confident enough to get on that board and start plugging and playing with wires and actually putting pieces together, which is kind of the point. So with that being said, this is it. This is the end. This is the end of the first block of instruction, the first 2 weeks in this Power Circuits and Transformers block. All right, we've gone through this entire thick, crazy book that when it first started, you probably said like, oh my God, that, we're going to skim over that, right? We've talked about every bit of math that's on this board and then some. There's actually some impedance formulas on here for parallel impedance and parallel circuits that I didn't put on here. And another one, I can't even remember. This isn't even everything you've covered in the first 2 weeks, but you've done everything on here. We talked about basics of Ohm's law to equivalent resistances in series and parallel circuits, which was day 1. Then we went over and talked about it with some AC power, kind of transferred over into day 2, where we started analyzing this right here, these phase angle relationships in a sine wave. Then back over to here to day 3 and 4, where we talked about capacitance and inductance in circuits, and we talked about those capacitive inductive reactances that are occurring because of alternating current and how those are affecting the circuit altogether. Then we brought that home with our vector math, which is just blowing us away, right? And we started talking about phasors and vectors to see why impedance is actually the total opposition to current flow, which is taking into account resistive elements and the reactant elements. All right? Then we hit home with unit 6, which was probably like the greatest unit ever, and we start talking about this crazy square root of 3 thing and like why these power calculations. You've got to know these power calculations. One thing you can just beat into your head is how to do three-phase and single-phase power calculations, because it is so relevant and so important to you moving forward in any job that you're going to go to that you have anything to do with electricity and understanding load requirements. All right, then after that, we started talking about transformers, right? This should have been the code down. Should have been good, like just kind of easy, understanding that science that's going in there. We talked about those transformer ratios going back and forth, right? And voltage ratios and current ratios. You know, and then we talked about some special configurations, right? And we talked about paralleling transformers together. We talked about the auto transformer. That's kind of a cool concept there too. And we talked about that basic distribution transformer, that one can of three up there that we see, and how that kind of works. How can we put that concept together with that open delta, or not open delta, but with that auto transformer connection and say, okay, I understand how they're going together. And then for the last thing, we just say, hey, let's put all this together. Let's bank a bunch of these together, and let's build a three-phase transformer bank, and let's play around and see what our voltages are so we can validate the science. And again, that 30-degree offset that's created between certain configurations, and why 1.73 is a thing, even in transformers. So again, hey, I hope these videos help. I hope you can go back to these, and they can provide that supplement to you where you take the lecture that you got in the class, you watch the video, you read the material, you do the labs, you do the quizzes, and you put it all together. None of these things independently should get you there. But when you combine them all together, you should have these aha moments. And if you don't, please ask, please get some help, and let's go forward. So good luck on your first test, and get ready for the next one, because it don't get any easier. Thank you.